Hi guys, BuildZoid here, and today we're going to be taking a look at a GTX 570 DirectCU2. And you might be like, BuildZoid, why the hell are we looking at a card from like 2011? And I actually don't know when exactly the 500 series released, but I think that's around the right year. So we're looking at this because it's a piece of fan mail I got, and also because Fermi cards are freaking awesome to overclock. In my opinion, like seriously, they're really really fun because it's before Nvidia introduced all of the different restrictions, and I got this as a piece of fan mail, and I have some pretty bad ideas for what I'm gonna do with it. And I don't actually want to e-power it because I don't have I'd have to pull an e-power off of one of my other cards to do it. So I have other plans for this that are in my opinion interesting. Anyway, let's first talk about the PCB here, and then talk about what I'm actually planning to do. So ASUS DirectCU2 cards are actually kind of neat if you're going to be overclocking like older generation stuff just for fun basically. Because they're not generally they're better than the reference cards that you can get. So for example, GTX 570s, normally the reference cards have a 4-phase V-core. This, on the other hand, has a 6-phase V-core. So that's a nice little upgrade. And then above that, we just have a memory VRM. And the funny thing is, Nvidia cards are very simple compared to like AMD cards where you have rails upon rails upon rails. Nvidia GPUs somehow get away with basically having a memory VRM, a V-core VRM, and then they'll have like a linear regulator for 1.8 volts over in this area. And I think this right here might also be something like 5 volts or something, but I'm not really that interested in those. Those are details like those are basically rails that are like if you're e-powering the card, you might have to force the card to keep them enabled, and that's about as interesting as they get because they're the kind of voltages where it's like if they're not present, the card won't run, but they don't really do anything anyway. So yeah, that's kind of that. Anyway, so yeah, we've got 2-phase memory power, 6-phase V-core. The V-core controller is this chip right here, which is unfortunately rebranded, but it's branded SHE. That is not an E, BuildZoid. What the hell was that? It's a branded SHE, which is an ASUS it's the thing ASUS used before they started branding everything Digi Plus, and it's an ASP 0907. This is probably a UPI semiconductor controller because all of the drivers here are UPI semiconductor. So these right here are UP, and I don't know why I pulled that line that far. Those are UP 6282 BDs. And these are dual drivers, so you have 2 PWM signals go in, 2 phases go out, which is why we only have 3 drivers in total, which initially you might be like, oh, it's a 3-phase. Nah, it's actually a 6. It's just that these chips replace, they basically act as 2 drivers built into one chip. So that's kind of neat, and that's how ASUS manages to get a 6-phase out of this, even though you only have what looks like a 3-phase set of drivers. What else is there? So that's kind of the V-core VRM control situation. The actual MOSFETs are these lovely things, which, it's a kind of an odd MOSFET package. I'm not really, you don't really see it on modern cards, but back in the day, it was really popular on motherboards and GPUs, and I think it's because you could only get, the higher power capability MOSFETs actually just came in this package instead of other packages, though these days you can actually get I can't remember the name of the package right now, but they're these days you can get MOSFETs with this level of performance or better in just completely standard lower profile packages than this anyway. So yeah, that's why you don't see these anymore. Anyway, these MOSFETs are pH, so the high sides, so you have a high side and 2 low sides in each phase, which is pretty standard way of getting more current handling capability. The high sides are pH 7030 ALs, which these are MOSFETs from Nexperia Semiconductor. I have no idea what the tablet is doing today. Yeah, so these are MOSFETs from Nexperia Semiconductor, and it's kind of that. So NXP 7030 ALs. These are really actually for GPUs of this era, even like 400 series GPUs, this is a really common high side MOSFET. And then for the low side, we're looking at a pair of 5030s. So, and these kind of suck. So the high side, I mean, by modern high side MOSFET standards, these are really slow. The low side is even worse though, because these are 5030 ALs, also an Xperia. Of course, like, why would you use two different brands of MOSFET? But these are 5 milliohm RDS on 10 volts gate to source voltage. These suck. Like, these are really bad. And ASUS is actually running two of them in parallel, and it's just like, that really doesn't help very much. So the end result is that the efficiency of this VRM is just, well, by modern VRM standards, it's god-awful. So 1.2 volts out, 200 kilohertz switching frequency, because again, the high sides are slow, so I'm assuming they're not running the VRM very fast. I will be making sure that it's running at like 200 kilohertz. Well, at most it would be running 300 kilohertz, but that would make the VRM significantly less efficient, so it probably isn't running above 200. But anyway, so 1.2 volts, 200 kilohertz switching frequency, and 10 volts gate to source voltage. The VRM would be pushing 150 amps output while producing 31 watts of heat, which is just like awful. Like, that is absolutely terrible. You know, like, yeah, modern VRMs have made me very biased against this right here. Because these days you can do 150 amps output at like 12 watts of heat, no problem. And this is just like, oh yeah. Yeah, no, this is terrible. Interestingly enough, the 5030s have 175 degrees. It's degrees Celsius, isn't it? Yeah. 175 degrees Celsius TJ max. So that's the maximum junction temperature. Now, so technically, like, these MOSFETs can run really, really hot. The thing is, these can't. These are still 150 degrees Celsius TJ max. Your capacitors are just like, these are 5,000 hours rated APAC capacitors, so those are good for 105 degrees for 5,000 hours. These are good at 105 degrees for 5,000 hours. These are SMD polymers. Those are probably only good for 2,000 hours at 105. So it's just like, yeah, if like this part of the VRM is at over 140 degrees Celsius, which is not a problem for these, what do you think the rest of the VRM is at in terms of temperature? So it's just like, yeah, that's very nice that you have these high temperature MOSFETs. It's just that everything around them kind of can't deal with that anyway, so not really that useful. Then you have 200, so anyway, 200 amps output, this VRM would produce about 51 watts of heat, which is just like, it doesn't get better. I mean, what did you expect? As the current output increases, the heat output goes with it. 250 amps output, the efficiency goes down as well. So 250 amps, it'll produce 74 watts of heat, and 300 amps output, it'll produce 102 watts of heat. Like, it's just gonna run insanely freaking hot. And so when I realized, like, initially when I saw this, I was like, oh, it's not a reference card. It should have somewhat decent power, like decent MOSFETs. And then I'm like, oh, these suck. This is like so bad. I'd actually like I'd actually like that. There's a pretty good chance I'll end up e-powering this anyway. But before I do that, to this card, there is one thing I want to try with this, because this is a great opportunity to test it. I have a GTX 480 with this style of MOSFET as well, like this MOSFET package, except that GTX 480 doesn't use the PH5030. That uses a PH 3030. And at this point, you could probably guess that this right here actually is a RDS on indicator. So the 3030s are 3 milliohm RDS on, which means they're more efficient. And so just for so basically, what I'm thinking of doing is I'm going to steal all of the 5030 3030s off of the GTX 480 I have, because I want to e-power that card anyway. That's getting e-powered basically regardless of what else. And so, and also there's like a 7030, like that also has 7030 high sides, and I have a VRM that's missing a 7030. So it's like, okay, I'm going to steal the 7030 off of that as a spare part. And then it's like, okay, well, since I'll disable the VRM anyway, I'll steal all of the PH3030s and swap them onto this card. If that works, theoretically, the efficiency would go from, 200 amps putting out 51 watts of heat. It could do 200 amps while producing 41 watts of heat, which is still really ridiculously hot, but less so than 51. 250 amps would, and I think I might need a new tip for my stylus, because I lean it too far and then it doesn't draw. So 250 amps, or I might just be holding it weird. 250 amps, instead of kicking out 74 watts of heat, would produce 59, which is, that's a significant improvement right there. And then 300 amps output, instead of producing, 102 watts of heat, would produce just 80, which is still ridiculously high. So the thing is, I actually don't know exactly how much power GTX 570s pull, but this card might be a pretty good card to figure that out with, because it looks like ASUS has all of the power delivery actually sort of separated. So what I mean by that is, like, we've got this inductor here. So if I wanted to just measure how much current is going through that inductor and into, I assume it's going to be like 3 phases of the VR. Actually, it's probably more like, no, because it looks like that feeds into this power plane right here. And that's bridged over here to there. So the thing is basically you can see that you have, these 3 phases run off of the 8-pin connector. And then the 6-pin powers these 3 phases. So I'm thinking, well, I can just put a wire, basically, or a shunt resistor. Actually, a shunt resistor is going to be better. I can just put a shunt resistor in between this like where this inductor was, or, well, I lift one side of the inductor up, put a shunt resistor from there to the output, and I can actually measure how much power is going into the V-Core VRM exclusively, and then we can get an idea of, like, just how much power does a GTX 570 actually pull, because I've not actually measured that. Like, I know the cards pull a lot of power, but the thing is, the memory VRM is basically 1/3 of the V-Core, so it's like, the memory system on these might not be particularly power. Like, the memory controller plus the GDDR5 might actually pull a pretty substantial amount of power, especially since this is like an older generation of GDDR5 than what you'd find on later cards. Though, judging by a HD 7970's memory system, or a 7950, I can't remember what I did it on, but it's a 7950. Yeah, it was a 7950. So I measured the memory power consumption on a 7950 of, like, VDDR. And so the VMem rail, it wasn't actually that high. The thing is, I'm not sure if there's, like, a big difference between how AMD's memory controller works and Nvidia's works, and if Nvidia's is very different, then Nvidia's memory controller might actually pull a ridiculous amount of VMem power. Instead of, like, on the AMD one, I think it was like 15 or 20 watts of VMem. Here it could maybe be 30, 40, 50 watts of VMem, right? Because this VRM is really rather substantial, and the whole card is from reviews on the internet of GTX 570s, these things pull regularly over 200 watts. So it's just like, well, this doesn't really look like it's going to do that great if it was outputting, well, this VRM can't really do over 200 amps that great. So I really wonder, like, a significant amount of power basically has to be going through the memory VRM. Unfortunately, that doesn't change the fact that I don't really care that much about the memory VRM efficiency, so I didn't actually bother to calculate it. Though, you can just go 50, because the thing is, it does use the same MOSFETs as the V-Core, so you've got you've got 2 low sides again, 1 high side, and they're again 5030s and 7030s, so you can actually just take the figures I have, like, you can take just this, divide that by 3, and you get the efficiency for 50 amps output at, it's going to be what, like 10 watts, which is like, that's pretty hot. That's actually pretty damn hot for 10 watts in just this much surface area, but depends how much airflow you shove at it, right? And I don't think it'll actually be pushing 50 amps into the memory system, so that's like, that's a lot of current. for memory to pull. Anyway, the controller for the memory VRM is a UP, and yeah, I keep doing that. That's a UP6223 controller, so that's not rebranded, and that is a two-phase. So it is a real two-phase VRM, but I mean, that's not really that surprising. Two-phase controllers are rather cheap. So yeah, other than that, ASUS does have a bunch of input fuses to protect the card from, you know, catastrophic failure. Like, the main thing that the fuses prevent is if your high-side MOSFET dies, which isn't really that rare as a malfunction for a VRM. Like, if a VRM is going to blow up, there's a pretty good chance your high-side MOSFET is going to fail closed, and it's basically going to short 12 volts to the output. And the fuse in that scenario, if the fuse blows fast enough, it can actually protect the GPU core from taking like serious damage by overvoltage. Because if you blip, say, 2 volts for like a couple milliseconds into a GPU core at ambient temperatures, it's dead. Okay, it's not even like it's dead. Well, if you go it kind of depends on the core as well, but basically somewhere around 2 volts to like 3 volts, somewhere in that range, it's dead. So the good thing is, so basically if you have a high side fail, hopefully the fuse blows up before the output of the VRM gets too high voltage. The other thing that the fuses prevent is if you're an idiot user and you have a card where the vCore VRM blows up, with the high side MOSFET failing closed, if you power cycle the card, you're not going to cause more damage, because if you didn't have that fuse and you tried to power cycle the card, it would actually just, like, the output voltage of the VRM would go way up before the overcurrent protection or short circuit protection of your power supply trips. And again, like, you'd just be blipping very high voltage into the core. And if you do that enough times, if the core was working before, well, after 6 or 7 attempts to, you know, power cycle it, it won't work anymore, depending on just how high the voltage was getting. And actually the number of attempts I pulled was completely random. Like, it might take 30, it might take 2, right? Like, I don't know. It really depends on how high the voltage on the output is getting. And also somewhat luck. Like, some cores might withstand a few more attempts by a few more, you know, bursts of high voltage than other cores. So that's kind of the thing that the fuses do help with. But ultimately, unless you're capable of repair, like, what the fuses don't do is they don't protect the VRM. Okay, like, the fuse is there basically so that you don't cause more damage after there is already a ton of damage done. So it's not really useful. Like, if you don't know how to repair stuff, the fuse doesn't really do anything for you. And even if you do know how to repair stuff, there's a good chance that the high side MOSFET blows up and shorts several layers, and it's just like, well, the fuse really, like, it stops you from, you know, making the short circuit even worse, but it doesn't change the fact that there's a crater in the PCB. So that's kind of the thing with the fuses, is they're kind of limited in terms of how useful they are. Like, I wouldn't consider them, like, if you're not capable of repairing things yourself, they're kind of useless. Right? Though if you are, like, looking for dead GPUs to buy, and you know certain cards come with fuses on them, then those are a safer purchase than cards that, you know, don't have fuses on them, because if they don't have fuses on them, then for all you know, whoever the owner of the card might have tried to power cycle it like a dozen times, and it's now really, really dead. So that's kind of the thing. Anyway, for my experiments with this card, I'm actually going to be removing all of the fuses, because I do really want to push, like, I do want to see just how far I can push the card, so I don't really want these blowing up during overclocking, because they'll blow up for even, like, sustained load, because that right there is some idiot didn't put it into my notes what these fuses are, but I want to say that's a 10 amp, and then they have 2 10 amps in parallel over here, and then they have another 10 amp down here. Yeah, I think that's a 10. So, and then they have another 10 amp fuse down here by the PCIe slot. So that's like well, for the PCIe slots, 10 amps is a bit high, but for the 6-pin, that's actually completely fine to have a 10 amp, and 2 10 amp fuses in parallel for the 8-pin is also completely fine. Honestly, I would put 3 of them, but I think the fuses are being sized more based on what the VRM can handle, rather than, you know, concerns about the 8-pin. So, yeah. Which even then, I think, like, that's kind of optimistic. 240 watts through, because this is for half of the VRM. Like, yeah, 240 watts through this part. Yeah, no, you're not putting that safely through that part of the VRM. So Anyway, that's the front of the card. The back of the card is also rather interesting because we've got a ProAdlyzer. I hopefully pronounced that correctly. Anyway, we got one of these. These are cool because they're basically giant SMD film capacitors. Now, they're notorious for having a god-awful lifespan, and they fail due to high temperatures very quickly. Especially in laptops, they're kind of notorious for failing in those. But this card the previous owner actually had this card on water cooling the entire time, so this thing's probably just fine, because water cooling does an excellent job of keeping everything nice and cool, especially the GPU core, so yeah, the ProAdlyzer is pretty cool. The one thing that's annoying about the ProAdlyzer is that it does get in the way of any further cap modding quite a lot, actually. So yeah, and I'm kind of toying, maybe I would like to desolder it and replace it with like 3-terminal polymers or something. But at the same time, it's just like desolder. Like these suck to desolder because they have like, there's basically you have these massive strips of just like pad where it's just, that's what it's soldered to. And so, yeah, very, very annoying to desolder. And also it's right behind the core, which is like that's a heat sensitive area. So you don't really want to try to. So I'll probably leave that on there, but it's just like, yeah, I do want to mess around with cap modding on this card as well. And the ProAdlyzer is kind of cool because the thing, so I actually didn't mention why they're cool. So it's a giant cap. And the cool thing about these is they have really low ESR and really low ESL because they are, you know, they have that really large connection to the PCB. So they work really, really well. The only issue is that they're not very high endurance, and they also have a ton of capacitance. Like the whole idea behind ProAdlyzers is that normally how you see on the back of a GPU core, you'd normally see like lots of little multi-layer ceramics in varying sizes. Yeah, the whole idea behind the ProAdlyzer was that you can replace all of that with one big capacitor, and you know, it simplifies manufacturing drastically. And well, this is one of the few cards where this is actually well, not really. There's a couple cards from ASUS that actually do this. The funny thing is there's also a lot of like GTX 500 series and 400 series cards where you have ProAdlyzers, but instead of putting them behind the core, which is like the intended use of a ProAdlyzer, they'll put them like between the vCore VRM and the core, so that you'll have like ProAdlyzers up here and just like everywhere. They'll just put a bunch of them. And yeah, they're still really cool. It's just like this is one of the few cards I've seen where it's actually being used the way it's meant to be used. So that's kind of neat. Also down here we have a linear regulator for the PEX rail. So that's the PCIe interface rail. This might actually be useful for LN2 overclocking. It depends on the generation with Nvidia. I'm not sure about the 500 series. So yeah. Anyway, and actually the other thing with this VRM is even the actual like output of the vCore is kind of a rather nice mix of capacitors in my opinion. Like we've got some multi-layer ceramics. There's obviously more of those on the back. We've got the, you know, APAC aluminum polymers in the through-hole packaging. We've got some SMD aluminum polymers. And yeah, I'm a fan of that. Like this is the funny thing is actually on modern GPUs, you see like they don't really do this anymore on modern GPUs. Like you'll either see all polymer. Well, there are some that still do it a lot, but most GPUs these days, you'll either see all SMD polymers or all through-hole polymers, and then, you know, some amount of multi-layer ceramics. Which of course, even back then, like even on a card like this, like you can see that's what this is doing. But you won't see ProAdlyzers anymore because I guess it's mostly the I'm actually not sure why this. I assume it's just, well, they're not in production anymore, so I assume that they stopped making them because it was just like, well, they really don't last as long as the other capacitor types. So that's kind of that. But still, it's a cool little component. It's just like, yeah, it also isn't really that great. So yeah, that's the GTX 570 DirectCU 2. Huge thanks to the guy who sent the card in because it's going to be great SMD, so like it's going to be great hot air soldering practice because I'm going to be replacing all of those. I think I could even replace the memory, but I don't have, because the thing is the GTX 480 I'm stealing the MOSFETs off of is also a 6-phase, so it just about works out that I have exactly the correct number of MOSFETs, which means if I screw up and break one, then it's just like, well, I'm going to be screwed. So Yeah, because I won't have enough of them. And they don't make these anymore either. So it's like you can't even buy, I'm pretty sure you can't buy them new anymore. Like if you're buying them, you're buying them like used. Because yeah, like they as far as I know, these have been discontinued. So it's kind of that. Anyway, this will be a fun little project card to work on. It's just a issue of all the new hardware releases kind of getting in the way. Also, I think I've already delidded it. So the thing is with the 500 series Nvidia GPUs, you can actually delid the core, which is honestly like unless you're very careful about it. Like I've delidded basically every single 500 and 400 series card I own. All of them still work. So I'd say I'm pretty damn good at it, but like I've also heard of people just absolutely destroying cards in the process. So it's like, it's not recommended unless you're like practice on cards that you know suck first and then maybe do it on cards where it's like, I actually want this working. Because the thing is, there is just thermal paste under this. Like, these aren't soldered. This is just like, you've got a heat spreader, and there's thermal paste under that heat spreader, and it's just like, yeah, that, well, thermal paste, well, you know, going thermal paste, heat spreader, more thermal paste, not as good as just having thermal paste to heat sink. So, yeah, that's kind of that. That's the ASUS GTX 570 DirectCU 2. Better than a lot of, like, as far as GTX 570s go, I think this is actually one of the best options for a PCB. Because, again, like, the reference cards are, like, 4 phases. And actually, I had a different GTX 570. Actually, the GTX 570 was the first card I successfully e-powered, in the sense that it still worked after I attached the e-power, not in the sense that it was actually particularly great at overclocking after the e-power, because my solder, like, the way I attached it was actually kind of crap, so the amount of voltage drop I had was just absolutely insane, and it was terrible, but it did work. Like, it ran, it finished benchmarks, but it kind of sucked on the whole, thermal, like the actual well, it wasn't a very well done e-power. It was just like it worked, but that card was a 4-phase. Like, that thing was terrible compared to what we have right here. So yeah, and obviously, I'm not going to just desolder all the like, the thing is, I also want to take before and after temperatures and before and after efficiency of the card, which is going to be interesting. Well, these things don't really have power limits, so I can check the before and after efficiency by just setting the same voltage and running like Firestrike or something. So anyway, yeah, I have big plans for this thing. I love just older GPUs, especially like Fermi generation, because the Fermi generation of, and like, this is all the cards without the stupid boost algorithm, without any voltage restrictions. Admittedly, that doesn't necessarily mean that the voltage control is particularly easy to like get, but these cards complain less when you try to modify them than the modern Nvidia cards. So yeah, you know, if you want to get into like volt modding and that kind of thing, I think 500 series, 500 series, 400 series Nvidia is your best option, because the thing is, AMD GPUs in that time period, AMD GPUs used like really advanced digital voltage controllers, because AMD just loves their power delivery being ridiculously complex, and as a result, much more annoying to like work with. So yeah. Anyway, that's it for the video. Thanks to the guy who sent the card in. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what I do here with actually hardcore overclocking, I do have a Patreon where you can support me directly down in the description below. And then I also have a Teespring store where you can get shirts, stickers, posters, that kind of thing. There's a link to that down in the description below as well, and those help out with they help out with running the channel quite significantly, because it allows me to, you know, buy things like modding supplies and motherboards, CPUs, and all the other stuff I do here. So yeah, that's it for the video. Thanks for watching, and goodbye.